Hi everyone. For this video, I'm going to do something a little bit different. I am going to go over a bunch of synthesis practice problems, and we're going to deal with reactions that we learned about in this unit, carboxylic acid derivatives. Okay, this is, depending on when you're viewing this video, this could be the 5th video or maybe 6th or 7th, depending if I add anything else before this. But we do have enough tools, information to do some really interesting synthesis problems. Also, I actually neglected to tell how to make an anhydride. If you take a look at our ski slope, we definitely know how to make an acid chloride from a carboxylic acid. And we can make an ester and an amide from the acid chloride by adding an alcohol or an amine. But I never really showed you how to do this purple arrow, this one right here, acid chloride to anhydride. And we'll take care of that. That's actually a pretty easy reaction. And then if we have time, and only if we have time, I do want to look back at this nitrile formation using SOCl2. If you recall, I said SOCl2 in this case is acting like a dehydrating reagent to change an amide, a primary amide, to a nitrile, if we have some time. So what is different about this video is that besides doing synthesis problems, I'm going to go over this after video assessment. So for each video that I make a one-page sheet of practice problems. And don't worry, here are the syntheses that we're going to do together. Okay. So for this video, 06E20, which just for bookkeeping sake matches our video file here. Let's do the first one. And the first one is draw the missing reagent to make this anhydride. Oh, that's exactly what I was missing in the previous videos, how to do this. We have an acid chloride. Oh, by the way, if you don't have a copy of this, just pause the video and write this down. We're definitely making an anhydride, and I have not told you the reagent. But I think it's pretty obvious that we're going to add something to this acid chloride and attack this carbon right here. Kick out the leaving group. What do we want to attack that carbon with? We want something that looks like that. And actually, this is exactly what we want to attack the carbon with. This is reaction 6I, and we'll put it on this sheet here. Reaction 6I. How to make an anhydride. I'll do a simple example, and then we'll go back to this sheet of practice problems and we'll fill in that arrow. But basically, if you take an acid chloride, and let's make it an ethyl, there's your dot. It's a little bit different than what we're used to. If you recall, we had sections in this unit that say add an alcohol and we get an ester, or add an amine and we get an amide. In both those cases, your alcohol and the amine, you're going to have to remove a hydrogen at the very end to get it back to be neutral. We're not going to do the same thing for an anhydride. We're not going to add the neutral molecule. We're going to add actually the literal anion. And what anion am I going to choose? Well, for this case, I'll choose this anion. Well, it's going to be a carboxylate, and I'll make it different, right? A different R group. This is different because normally when we convert an acid chloride into one of the derivatives, we use a neutral molecule, like an alcohol to make the ester, an amine to make the amide. we're not using the carboxylic acid to make the anhydride, we're using actually the carboxylate. Remember how I said that this will become infinitely easier if you know how to identify molecules and verbalize. Because now, to make an anhydride, you don't add the carboxylic acid, you add the carboxylate, the anion form. And the mechanism is easy. I'm not going to even go through it. You could visualize it with me. The O comes in, you make the what intermediate? You make the tetrahedral intermediate. The double bond reforms and you kick out the chlorine. Anyway, here's your anhydride. So when we go to our practice problems, and I'll write it here, the answer. I call it a reagent, the thing over the arrow, but it's another starter material. This arrow equals, just have to match that, the carboxylate form, right, of this group here. Okay, that's your answer. That's what goes over the arrow. Pretty easy. Again, memorize acid chloride plus carboxylate gives you anhydride. We're done with question 1 on the practice problems sheet for this video. Let's go to syntheses. Okay, this is number 2. It's a synthesis, so we're gonna have to have a lot of space usually. What should I say? I'll just call this number 2. Okay. All right. I have this cyclic ester, and the synthesis is to convert it into this acyclic molecule. What does that suggest? Here's my analysis. First of all, there's only 1, 2, 3, 4 carbons here. But you notice in this target, we have 1, 2, 3, 4, 5, 6. We added 2 carbons. Do I know which carbons we added? No, not yet. What else I notice is that we broke the ring. So we had to cleave a bond to open ring. This is called a lactone. A lactone is the same thing as a cyclic. It's a fancy name for a cyclic ester. I'm going to have to do some ester chemistry, ester reactions. The way that I know how to open this, there are a couple ways. I could do a reduction. If I do a reduction, like lithium aluminum hydride, I will get a molecule that has 2 hydroxyl groups. And the problem is, well, first, I didn't add any carbons, so that's kind of a big problem. And the other problem is we have to oxidize one of the carbons. So probably we're not going to use lithium aluminum hydride to open up the ring. The 2 carbons I added, I hope you can tell. With practice, you will be able to tell pretty easily, but these are methyl groups. I don't have methyl groups anywhere on this molecule. So I really made this bond here, and I made this bond. I made carbon-carbon bonds. Maybe these 4 carbons, 1, 2, 3, 4, are these 4 carbons, 1, 2, 3, 4. Okay. Right now I'm not going to speculate which one is 1, which one's 2, which one's 3, and which one's 4. Okay. I can label them here, but I'm not going to yet label them on my target. What I'm going to focus on is that, I need to know how to make carbon-carbon bonds. The most popular way to make a carbon-carbon bond, if you recall in a previous unit, it was the organometallics. I tried to emphasize that It's the star of the organic chemistry world, how to make a carbon-carbon bond um, using a Grignard or organolithium. Hmm. Look at these two classes of molecules I have here, Grignard and ester. I'm going to take a chance, and I'm going to react this ester with the Grignard reagent. And let's see if I get anywhere close to my product. There's an oxygen here. I could get partial credit. If you're in my class, I will give you partial credit if you get the beginning of the synthesis correct. Or even if you get the end of the synthesis correct, I'll give you partial credit. But I'm going to start from at the beginning, okay? Because I want to break open this ring somehow. Well, I'm going to use Grignard. 1, methyl Grignard. Now the thing is, to do well in synthesis, the first step is to be a master at all the individual reactions. And we've had up to I. But not only that, you're expected to remember the main reactions from the previous units. Like, well, this Grignard plus ester is actually unit 6, so we did talk about it in this unit. But probably there's an oxidation, maybe, that we have to remember how to do from a previous unit. Like I said, you got to be really good at the individual reactions, knowing the reagents and the targets, the products, before you can start linking them together in a full synthesis. Because do you know how to draw the product if you're given this reaction? You add the Grignard twice to the carbonyl carbon, or the carbon of the C double bond oxygen, and you change that to an OH. But the thing is, when you kick out this group comes off and gets protonated and becomes an alcohol. I suggest if you don't know how this happens, okay, I'm going to swing this down over here. Carbon 1, 2, 3, 4. 1, 2, 3, 4. Look back at the video where we talked about Grignard plus ester, and you would hear me say that the Grignard adds twice. Those two carbons, those two methyls came from the Grignard reagent. In the synthesis, I allow my students to couple a protonation or deprotonation step under or over the same arrow as the previous reaction. So proton transfers, I don't write separately. Okay, you could do a 1-2. Okay. Are we near the product? We're almost there. We could oxidize it, and you notice that this is tertiary alcohol. Tertiary alcohols cannot be oxidized, but primary alcohols can. And here we're going to use, I'm partial to potassium dichromate with sulfuric acid. This is Jones oxidation. You're going to oxidize the primary alcohol all the way up to the carboxylic acid. Well, what is hard about this problem? What's hard about this problem is maybe you thought that carbon 1, the one with the C double bond oxygen, would be carbon 1 here of the carboxyl group, but actually it's carbon number 4. So our numbering here, actually, this is 1, this is 2, this is 3, this is 4. Okay. This is not easy. Okay, we have to know what reactions of an ester are available. That's why a roadmap where we have an ester in the middle, and we do all the reactions: hydrolysis, reduction, Grignard, adding an alcohol, adding an amine. Yes, adding an alcohol, adding an amine. Right now I just listed 5 reactions that use an ester. The other thing that makes this a little bit more difficult is the ester cyclic. Okay, meaning that the group that got kicked out, right, is still connected, right? This was the group that got kicked out because this bond broke. right there. Okay, the leaving groups is actually still connected. That was a doozy. Okay, it was only 2 reactions, but it did require a lot of thinking. Let me show you the next one. This one right here. This one might be a little bit easier. Our analysis is we made a what? We made an amide. So again, think back to this ski slope. How are some ways we can make an amide? If you recall, I said acid chloride is the best way to get to the amide because this is very reactive, and all we have to do is add an amine to go from here to the amide. Now our task is to recognize what kind of amine and what kind of acid chloride. So I'm going to show you now a different strategy. Instead of looking at the starting material and try to figure out all the different reactions to use at the beginning, let me show you a strategy of working backwards. Okay. Yeah, let me start a new sheet. Okay. The synthesis is this. We start out with, oh, what is all this? We start out with this ring. The other thing about synthesis is don't get distracted by functional groups that you feel that aren't really important for the synthesis. And what I mean by that is don't let this nitrogen distract you. Because all of the action, I think, is taking place with this bromine at the alkyl halide part of the molecule. So let me show you how to work backwards. My answers are going to be in blue. My notes are going to be in pink and green. And my analysis is that we have an amide. This kind of arrow, okay, normally I don't grade this. I grade the synthesis, the one I'm going to draw in blue, right? I don't grade the strategy, or I don't grade the annotations, but obviously the annotations helped us a lot when we're doing this synthesis. This is strategy. Okay, I'm not expecting the grader to look at this. How do I make an amide? This kind of arrow is called a comes from arrow. It's a retrosynthetic arrow, is how the textbook would explain it. This is a product. I said, what do I need? What kind of starting materials do I need to make this product? Eventually, I hope I could backtrack all the way to the starting material that the problem wants me to use. But forget about the starting material here. How do I make an amide? You make an amide from the acid chloride and the amine. And the combination I want to use is that acid chloride. What did the amine look like before it added to this carbon of the CO double bond? It looked like this, NH3. Okay, I'll draw a lone pair there. Remember the mechanism? The amine comes in, tetrahedral intermediate, you reform the double bond and you get chlorine. The thing is that nitrogen still had 3 hydrogens and it is plus. But when you add a neutral nucleophile, you remove the hydrogen at the very end to make it neutral. Okay, you know, if there was a 3rd hydrogen here, this would be positive. You don't want to get in the weeds with a mechanism when you want to do a synthesis. You see that I didn't draw any mechanism arrows. That's not what the problem is asking. The problem is asking for a synthesis. Before I go back, one last thing. I should have mentioned this. This is how I asked the synthesis problem. Your professor could say, provide an efficient synthesis, okay, and then obviously you'll string together a bunch of reactions. The way that I indicate that it's a synthesis problem is a question mark with 3 arrows, always 3 arrows. The 3 arrows doesn't mean anything. It doesn't indicate the number of reactions, okay? It just means that you're using more than one reaction, right? Okay. Like for instance, I wouldn't consider this a synthesis. I know we're synthesizing anhydride, but I really consider this a fill in the blank, a fill in the reagent, because it's only one reaction. Okay, enough stalling. Nuts. I'm not given an acid chloride. I have to make this. But I'm confident that if I can make this, I can make this. Okay. Now, if you don't know how to go from here to the acid chloride, then get your partial credit and draw. I'll do it now because actually I'm afraid of running out of time. I want to make sure that I get at least this partial credit here. I think that's all I need, right? Acid chlorides are pretty reactive. I don't need any heat. I don't even need a base because the chloride that gets kicked out will remove that extra hydrogen. Hopefully my professor is reasonable because I know how to make this product if I was given this acid chloride. If I ran out of time, I get points for this. I don't get points for the beginning. Let me at least draw the starter material. Maybe if I see it in blue, I can concentrate really hard and figure out how to get from here to here. How do I make an acid chloride? It's literally on our ski slope. It's right here. Carboxylic acid to the acid chloride. Oh, I'm still going to work backwards. I want to make this acid chloride from a carboxylic acid. Nitrogen. And my carboxylic acid looks like this. Okay. Even more partial credit. Now, this was a reaction in Unit 6. This was a reaction in Unit 5, but we definitely talked about it in Unit 6. What is this? This is from the unit where we talked about organometallics. Remember how to make a carboxylic acid? CO2. Oh, okay, let me write this down. Not quite yet. I have to do this from a Grignard. Okay, so this kind of got screwed up. Let's do this. The best way to make a carbon-carbon bond, and I keep forgetting this nitrogen, is through an organometallic. Okay, it's good. It looks a little bit messy. Okay, and it looks a little. The pathway is a little bit twisty, but alkyl halide converted to the Grignard, and now we do this. So hopefully my grader knows what I'm doing here. If not, if I'm a little worried about it, I would redraw this. But I think this is okay. It's still one line. Okay. And we take the Grignard reagent, we add carbon dioxide, make carboxylic acid. The carboxylic acid is converted into acid chloride, and like my strategy said, I know how to make an amide with an acid chloride and an amine. This happens to be ammonia. Okay. This is longer, but to tell you the truth, this is actually easier because we know, like, there was literally a reaction that told us how to make an amide, how to make an acid chloride, how to make a carboxylic acid from an alkyl halide. I think this is easier than this because, truthfully, this ring messes people up. People usually hate doing reactions on rings or doing syntheses where you have to either make a ring or break up a ring. Okay, so that one is great. This one is good because it kind of tests the full range of reactions in Unit 6. Let's do another one. We might have time for 2 of these, but let's at least start this one. This one's interesting because I give you 2 starter materials. I am forcing you to use both of these starter materials in tandem together somehow to create this molecule. This one's a little bit tricky. We have this OH plus, oh, it's not even an organic molecule. It's a salt, sodium cyanide. You'll see what I'm going to do with this in just a bit. Well, This looks a little weird. We have a cyanide. That's a C triple bond N, but we don't see a C triple bond N here. There had to have been a reduction. That comes from arrow. I'm thinking that I want to see where the CN is coming into play. CN looks like this, and I'm going to draw out the triple bond. Do you remember the reaction to go from here, the cyanide or the nitrile? It has two different names. Sodium cyanide to make the nitrile. But do you know how to go from the nitrile? Maybe if I write down the class of molecule, it will jog your memory to what? The OH is already there. Okay. Don't worry about the starting material. But I make a primary amine. That verbalization should trigger something in your memory. There aren't a lot of reactions that use a nitrile actually. So look in your roadmap. Hopefully you're making roadmaps and flashcards. Look how many reactions start with a nitrile. There aren't many. There's hydrolysis, and then there's reduction. So going in this direction, if I reduce this with LiAlH4, H2O, it's a reduction. What is this? Let me redraw it. Okay. This is the same as this molecule here. Maybe this will jog your memory. That's a cyanohydrin. What? Really did work with cyanohydrins? Yeah, we have. It's when you take a cyanide and you hit it with an aldehyde or ketone. This came from the aldehyde and ketone chapter. C nucleophiles. So where did this come from? Man, we're really taking advantage of retrosynthesis. I wasn't expecting to do this. But this came from this. Look in your aldehyde and ketone unit. C nucleophile comes in, mixes an OH. You know what's weird about this synthesis? I had an OH here, but I gotta get rid of that OH. I gotta make it into an aldehyde first, and I'll get it back later. See, that's one of the tricky things about synthesis. Just because you see the same thing in the product, in the target, as you do in the starting material, doesn't mean that that is the same O, or that is the same functional group. See, I don't have a hydroxyl group here. And we should know how to go from here to here. That's my plan. That's my retrosynthetic analysis. My synthesis is this. This one is a good one too. Okay. I'm going to use now my NaCN. And we do have to protonate it. So either with water or H3O+. What are we protonating? Look at our plan. We have to make the cyanohydrin. And we have this. Again, to be good at synthesis, to use your tools, you got to be an expert at each individual tool. You have to master each individual reaction, or else this is not going to flow very easily. Okay? Use your roadmaps, use your flashcards. What's our plan here? Oh, reduction. It's a pretty sophisticated, I think, sophisticated synthesis. Mainly because, I hope I really did this right. Mainly because this is a siren. It's kind of tempting you to say, always keep this OH because we need it. But if you try to keep it, there's actually no way to put stuff here on this carbon when you have a hydroxyl group. You have to use the carbonyl group, right? And we could do a lot of additions now on the carbonyl, and we get back the OH. This is the answer. I think this is the most efficient synthesis for this problem here. Let me just double check. PCC to aldehyde. Aldehyde plus cyanide gives you the cyanohydrin. And we reduce the triple bond into a single bond. This is from unit 6. Okay, so for this synthesis, we only had one unit 6 reaction. I'm I gotta go. I don't want to have these videos last more than 30 minutes or too far over 30 minutes. But again, for my class, you have these available. Okay, so we have the answer key up to here, and I'll provide the answer for this a bit later. And then there's one more problem for this video. Um, it's a good word problem. It takes a look at a real drug molecule, lovastatin, and it asks you, how do you make this? Particularly, how do you make the esters and the cyclic ester, which is a lactone. Cyclic esters are lactones. Okay. Right? You're now a pharmaceutical chemist and trying to figure out what are your starting materials to make your multi-billion-dollar drug. So that's that. Um, for people who are not in my class, like I said, I do have these video assessments for each video. Okay. If you want any of these, okay, so here's the advertisement. If you want any of these, just put a comment or send me I don't know how else you could contact me. Send me a comment on YouTube, and I could get you these different assessments for each video. Yeah. All right. I will see you guys later.